Tonight, we're going to the edge of our own solar system, to the frozen, violent, barely explored region sitting just beyond Neptune, the Kuiper Belt. It triggered one of the most destructive events in the history of this planet. It is the source of every short-period comet that has ever crossed Earth's sky. It contains worlds so geologically complex that when we finally sent a spacecraft past one of them, scientists didn't know what they were looking at. And somewhere in its outermost reaches, something may be moving that we still haven't found. By the end of tonight, you're going to see exactly what this place is, what it unleashed on the early solar system, and why the space beyond Neptune is nowhere near as empty or as safe as it looks. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Picture our solar system the way most people imagine it. The Sun at the center. 8 planets orbiting in neat concentric rings. Empty space between them. Everything orderly, stable, predictable. That picture is wrong. Not wrong in its basic facts, but wrong in what it leaves out. Because beyond Neptune, beyond the last recognizable planet, there is an enormous region of space that contains hundreds of thousands of objects, some of them worlds in their own right, all of them frozen, all of them ancient, and all of them orbiting in conditions so extreme that we're still working out what the rules even are out there. That region is the Kuiper Belt. It stretches from about 30 astronomical units from the Sun all the way out to roughly 50 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, approximately 93 million miles. So, the Kuiper Belt begins, where Neptune's orbit ends and extends another 1,860,000,000 miles beyond that. The entire distance from the Sun to Neptune is roughly 2.8 billion miles. The Kuiper Belt adds almost another 2 billion miles on top of that. It is not a gap at the edge of our solar system. It is a vast, populated, dangerous, and barely understood region that we have only just begun to explore. And the reason it exists at all, the reason it has the shape it has and contains the objects it contains, is one of the most dramatic stories in planetary science. To understand why the Kuiper Belt exists, you have to go back 4.5 billion years. The solar system didn't begin as planets. It began as a cloud. A vast, slowly rotating cloud of gas and dust, mostly hydrogen and helium, with small amounts of heavier elements scattered throughout. Oxygen, carbon, nitrogen, iron, silica, the residue of older stars that lived and ended before our Sun ever formed. When something disturbed that cloud, probably a shock wave from a nearby stellar explosion, it began to collapse under its own gravity. As it collapsed, it spun faster. Conservation of angular momentum. The same principle that makes a figure skater spin faster when they pull their arms inward. The cloud had a tiny net rotation to begin with, and as it compressed, that rotation amplified. The result was a flat, spinning disk of material around a hot, dense center where the Sun was forming. In the inner disk, close to the forming Sun where temperatures were high, only rocky materials could survive. Ice evaporated. Volatile compounds boiled away. What remained were grains of rock and metal, slowly clumping together, growing from dust into pebbles, from pebbles into boulders, from boulders into the rocky planets we know today. Farther out, where temperatures were cold enough for ices to remain solid, the story was different. water ice, methane ice, ammonia ice, carbon monoxide ice. All of these could survive and accumulate. The building blocks of worlds out here weren't just rock. They were ice mixed with rock, frozen chemistry from the original solar nebula. These icy building blocks began to clump together too. And for a while, in the outer solar system, the same process that built Mercury and Venus and Earth was happening on a grander scale. Worlds were forming, big ones: Jupiter, Saturn, Uranus, Neptune. But here's where the story gets complicated. As the giant planets grew, their gravity didn't just help things accumulate. It also threw things apart. Jupiter is a gravitational bully. There is no better way to describe it. At roughly 318 times Earth's mass, Jupiter dominates the dynamics of the outer solar system in ways that are almost impossible to overstate. Every small body that drifted too close to Jupiter during the early solar system faced a choice it didn't get to make. It would either be flung inward toward the Sun, accelerated outward into deep space, or locked into a specific orbital relationship with the giant planet. Saturn did the same. Uranus, Neptune. Each of these giants, as they grew and as they migrated through the early solar system, scattered the smaller icy bodies that had been accumulating in the outer disk. Some were launched clean out of the solar system, ejected into interstellar space, gone forever. Some were thrown into the inner solar system, where they became comets and asteroids, some of them contributing to the heavy bombardment that shaped the early surfaces of Earth and the other rocky planets. And some settled, not into neat orbits, but into a broad, scattered, gravitationally jostled region beyond Neptune. That is the Kuiper Belt. It is not a pristine, undisturbed place. It is a graveyard. The remnant of a population of objects that was once far larger, far more densely packed, and that lost most of its members to the chaos of the early solar system's formation. Current estimates suggest the Kuiper Belt today contains less than 0.1% of the material that was originally out there. The rest was ejected, destroyed, or absorbed. What remains are the survivors, the objects that found stable enough orbits to persist for 4.5 billion years without being flung away or consumed, and there are a lot of them. Astronomers estimate there are at least 100,000 Kuiper Belt objects larger than 60 miles across. The total count of objects larger than about half a mile across may be in the hundreds of millions. This is not empty space. People sometimes imagine the Kuiper Belt as a dense cloud of material, like a thick fog of asteroids you'd have to navigate around. It's not that either. The Kuiper Belt is enormous. The volume it occupies is staggering. And within that volume, the objects are spread so thin that you could pass through the entire belt without coming anywhere near a single one. The average distance between Kuiper Belt objects is tens of millions of miles. But the total number of objects still makes it the most densely populated region of the solar system beyond the asteroid belt. And the sizes of some of these objects will recalibrate what you think of when you hear the words edge of the solar system. Pluto is out there. Pluto is a Kuiper Belt object. That is what it is. Not a failed planet. Not a small, sad world demoted by bureaucracy. A Kuiper Belt object, one of the largest known members of a vast population of icy worlds beyond Neptune. Pluto orbits the Sun at an average distance of about 39 astronomical units. Its orbit is tilted about 17 degrees relative to the plane of the solar system, which is already a clue that its history involved gravitational interactions that pushed it around. Pluto takes 248 years to complete one orbit of the Sun. When NASA's New Horizons spacecraft flew past Pluto in July of 2015, it sent back images that stopped planetary scientists in their tracks. Nobody expected what they found. Pluto has mountains, real mountains, made of water ice, reaching heights of around 11,000 feet above the surrounding terrain. It has vast plains of frozen nitrogen that appear to be convecting, slowly churning as warmer material from below rises and cooler material at the surface sinks like a slow-motion lava lamp made of ice. These convection cells can be hundreds of miles across. They move at an imperceptible crawl, cycling on timescales of millions of years. But they are moving, right now, on a world in the outer reaches of the solar system, billions of miles from the nearest source of meaningful heat. It has a region called Tumbar Regio, an enormous heart-shaped pale formation spanning roughly 1,000 miles. One of the most visually distinctive features in the outer solar system. Its unusual brightness comes from frozen nitrogen that has pooled in a low-lying basin. As sunlight, faint as it is at Pluto's distance, warms the surface slightly, the nitrogen sublimates, moves through the thin atmosphere, and redeposits in colder, shadowed regions. It is a weather system. On Pluto. Pluto has a thin atmosphere of nitrogen, methane, and carbon monoxide. It extends upward from the surface for roughly 1,000 miles. The atmosphere is so thin that the surface pressure is about 100,000 times lower than sea level pressure on Earth. You couldn't breathe it. You wouldn't even register it on your skin. But it exists, and it has layers, and it interacts with the sun's ultraviolet radiation to produce haze at multiple altitudes. A blue haze that photographs from New Horizons showed as a faint ring of color against the black sky. Pluto is blue-hazed, mountain-rimmed, nitrogen plain-covered, and may have ice volcanoes. Structures that appear to have erupted not with molten rock, but with a slurry of water, ammonia, and methane, extruding frozen material onto the surface. Pluto is geologically active. It should not be. At 39 astronomical units from the Sun, receiving only about 1/600th the sunlight Earth does, with surface temperatures hovering around -370 degrees Fahrenheit, or about -223 degrees Celsius. There should be essentially no energy to drive geological activity. And yet, there it is. Scientists believe the answer involves Pluto's interior retaining heat from its formation, possibly combined with tidal heating from its large moon Charon, and possibly from the decay of radioactive elements within the rock that makes up its core. The exact mechanism is still being worked out. Charon itself deserves mention. Charon is enormous relative to Pluto, about half of Pluto's diameter, roughly 750 miles across. The mass ratio between Pluto and Charon is close enough that they don't orbit a point inside Pluto. They orbit a point in the space between them, a common center of mass that sits outside Pluto's surface. This makes Pluto and Charon a double dwarf planet system, two worlds orbiting each other. They are tidally locked to each other, meaning the same face of Pluto always faces Charon, and the same face of Charon always faces Pluto. If you stood on Pluto's Charon-facing hemisphere, Charon would hang motionless in the sky, never rising, never setting. If you stood on the opposite hemisphere, you would never see Charon at all. Charon also has its own surface features. A vast reddish polar cap, nicknamed Mordor Macula, whose color comes from tholins. organic compounds that formed from ultraviolet processing of methane gas that escaped from Pluto's atmosphere and settled on Charon's polar regions. Pluto's own escaped atmosphere is staining Charon's poles from across the space between them. Pluto has 4 additional small moons beyond Charon: Styx, Nix, Kerberos, and Hydra. All of them thought to be fragments from a giant collision early in the solar system's history, when a large object struck the body that would become Pluto and the debris coalesced into moons. The key point in all of this is that Pluto is a world, not a rock, not a frozen lump, a complex, layered, geologically active world with an atmosphere, with weather, with surface features as varied as anything in the inner solar system. And it is not even the most interesting thing out there. Eris is. Eris was discovered in 2003 and formally described in 2005. It sits much farther out than Pluto. Its highly elliptical orbit takes it as close as 38 astronomical units to the Sun at its nearest point, and as far as 97 astronomical units at its most distant. At its farthest, Eris is more than twice as far from the Sun as Pluto ever gets. Eris is slightly smaller than Pluto in terms of radius, about 1,445 miles across, compared to Pluto's 1,477 miles. But Eris is more massive. About 27% more massive than Pluto. That means Eris is significantly denser, suggesting it has a higher proportion of rock relative to ice in its interior. At 97 astronomical units from the Sun, Eris receives so little sunlight that its surface temperature sits somewhere around -360 degrees Fahrenheit, or about -218 degrees Celsius. And yet spectroscopic observations show that Eris's surface is covered in a thin layer of frozen methane, some of the most reflective material in the solar system. Eris reflects about 96% of the sunlight that hits it. For reference, fresh snow reflects somewhere between 80 and 90%. Eris is whiter than fresh snow. The leading explanation is that, as Eris moves to the distant, cold parts of its orbit, its thin methane atmosphere freezes out and settles onto the surface as frost. When it swings back closer to the Sun, that frost sublimates and the atmosphere temporarily reforms. A world with a seasonal atmosphere, on a 559-year orbital cycle. Each time Eris rounds the inner part of its orbit, it briefly becomes a world with weather. Methane snowing down onto the surface. Then, as it retreats back into the dark, the atmosphere collapses again. The frost remains. The surface gleams white until the next time around. Eris has one known moon, Dysnomia, discovered in 2005, shortly after Eris itself was identified. Dysnomia is roughly 270 miles across and orbits Eris once every 15.8 days. The system is tidally locked, with the same face of Eris perpetually facing Dysnomia. Studying Dysnomia's orbit allowed astronomers to calculate Eris's mass precisely. That's how they established that Eris, despite being smaller than Pluto in radius, is denser and heavier. Eris was what directly caused Pluto to be reclassified. When an object comparable in size and mass to Pluto was found orbiting the Sun, the question of what exactly a planet is became impossible to avoid. The International Astronomical Union defined a planet as an object that orbits the Sun, has sufficient mass for self-gravity to pull it into a roughly spherical shape, and has cleared the neighborhood around its orbit. Pluto, Eris, and everything else in the Kuiper Belt fail the third criterion. They haven't cleared their orbits. The Kuiper Belt is full of objects, and Pluto is just one of them. So Pluto was reclassified, not diminished, not erased, just correctly placed in its context. It is a dwarf planet. So is Eris. So is Makemake. So is Haumea. And there are likely dozens more out there that we haven't measured precisely enough yet to confirm. Makemake orbits the Sun at an average distance of about 45.5 astronomical units. It takes 306 years to complete one orbit. Makemake is smaller than Pluto, roughly 880 miles across. Its surface is covered in frozen methane and ethane, giving it a reddish-brown color. The coloring comes from the same process seen on other outer solar system bodies. Radiation from the Sun and from cosmic rays drives chemical reactions in the surface ices, producing complex organic compounds that absorb visible light and redden the surface. For a long time, Makemake was thought to have no moons. Then, in 2016, astronomers using the Hubble Space Telescope discovered a small moon orbiting it, nicknamed MK2, about 100 miles across, orbiting Makemake in a tilted, highly elliptical orbit that takes about 12 days to complete. The fact that MK2's orbit is so elongated and tilted suggests it wasn't formed gently alongside Makemake in the early solar system. It was probably captured, gravitationally snagged at some point in the past. MK2 is also very dark compared to Makemake. Makemake's high reflectivity comes from its fresh methane frost. MK2's low reflectivity suggests it doesn't retain the same frost, possibly because its surface gravity is low enough that gases sublimating from it escape to space rather than falling back as frost. The same object, the same place in the solar system, and yet two very different surfaces based on nothing more than size and gravity. We don't know when MK2 was captured. We don't know how. Another open question from a region full of them. Haumea is the strangest of the dwarf planets. It orbits the Sun at an average of 43 astronomical units and takes 285 years per orbit. At about 720 miles across, at its longest axis, it's smaller than Pluto. But Haumea is not round. It is shaped like a rugby ball or a slightly flattened American football, elongated along its longest axis, squashed at its poles. The reason is its rotation rate. Haumea spins once every 3.9 hours. That is extraordinarily fast for an object of its size. Earth, with a diameter of about 7,900 miles, takes 24 hours to rotate once. Haumea, with its 720-mile longest axis, rotates more than 6 times faster than Earth. The centrifugal effect of that rotation has deformed the body outward at its equator. It's being physically reshaped by its own spin. Haumea's longest axis is about twice as long as its shortest axis. If you viewed it from above its rotation pole, it would look elliptical. From the side, it would look stretched. It is a world that looks like nothing else in the solar system. That spin rate needs an explanation. Objects don't normally rotate that fast. The most widely accepted hypothesis is a large, ancient impact. Something hit Haumea so hard that it dramatically spun it up. The collision that caused this may have also scattered material across the Kuiper Belt, contributing to what's known as the Haumea family. The Haumea family is a cluster of Kuiper Belt objects with similar surface compositions and orbital characteristics. They're thought to be fragments from that same ancient impact, debris that ejected into space and spread along the orbit. Right now, pieces of Haumea are scattered across the outer solar system, separate objects with separate orbits. But they carry the same chemical fingerprint, the same spectroscopic signature, same ice, same colors, same origin. A collision billions of years ago that we can still read in the orbital patterns of objects today. Haumea also has a ring, discovered in 2017 when it passed in front of a background star, and the ring briefly blocked some of that star's light. Haumea is only one of a small number of trans-Neptunian objects confirmed to have a ring system. The ring sits at a distance of about 1,400 miles from Haumea's center. It is narrow, only about 43 miles wide, and Haumea has two moons, Hi'iaka and Namaka, both named after Hawaiian goddesses. Hi'iaka is about 200 miles across and orbits Haumea in about 49 days. Namaka is smaller and orbits closer in, with a period of about 18 days. Namaka's orbit is eccentric and precessing, meaning the orbit slowly rotates over time. The gravitational interaction between Hi'iaka and Namaka drives this precession. Two moons influencing each other's orbits around a world with a ring, all of it spinning at nearly 6 times Earth's rotation rate. For something sitting at 43 astronomical units from the Sun, in a place most people don't know exists, Haumea is genuinely remarkable. The Kuiper Belt is not homogeneous. Astronomers divide its population into distinct categories based on orbital behavior, and those categories tell a story about how objects got where they are. The classical Kuiper Belt objects, sometimes called cubewanos, after the designation of the first such object discovered, have relatively circular, low-inclination orbits between about 42 and 48 astronomical units. These are the objects that appear to have been least disturbed by Neptune's gravity. Their orbits suggest they formed more or less where they are today and haven't been significantly perturbed since. Within the classical belt, astronomers have further divided the population into cold and hot populations. This doesn't refer to temperature. In this context, hot and cold refer to orbital excitation. How much variation there is in inclination and eccentricity. Cold classical Kuiper Belt objects have nearly circular orbits close to the plane of the solar system. They're redder, on average. Their surfaces are covered in more pristine, radiation-processed material. They tend to be binary systems, two objects orbiting each other at a higher rate than the hot population. These binaries are thought to have formed together in the same region of the early disk through a process called gravitational collapse of a cloud of particles. If they had been violently scattered to their current locations, the binaries would have been disrupted. The fact that they persist as binaries tells us the cold classical objects stayed in place. Hot classical Kuiper Belt objects have more elliptical, more inclined orbits. They're bluer, on average. They look more like the scattered disk population. They were probably perturbed to their current orbits from somewhere closer to Neptune, scattered outward during the period of planetary migration, and then settling into orbits that appear stable over long timescales, but that betray their more violent history. Two populations, occupying the same region of space, with fundamentally different origins. Then there are the resonant Kuiper Belt objects. These are objects locked into specific gravitational relationships with Neptune. Pluto is the most famous example. Pluto is in what's called a 3-to-2 resonance with Neptune. For every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. This isn't a coincidence. It's a gravitational lock that has persisted for billions of years. Objects locked into this specific resonance with Neptune are called Plutinos. There are hundreds of known Plutinos, possibly thousands more, undiscovered. There are other resonances too. 2 to 1, 4 to 3, 5 to 3. Each one represents a population of objects that got locked into step with Neptune at some point in the past and has stayed there. The resonances are important because they tell us something about Neptune's history. The leading theory is that Neptune did not form where it currently orbits. It formed closer to the Sun, somewhere around 15 to 20 astronomical units, and migrated outward over millions of years as it exchanged momentum with the debris disk that surrounded it. As Neptune moved outward, it swept up objects into resonance with it, dragging them along. That is how Pluto ended up where it is. Pluto wasn't always in resonance with Neptune. Neptune found it. Neptune pulled it in. The 3-to-2 resonance is Neptune's gravitational fingerprint, pressed into the orbital structure of an entire class of worlds. Beyond the classical belt and the resonant objects, there is the scattered disk. This is where things get genuinely disturbing. The scattered disk is a loosely defined population of objects with highly elliptical, highly inclined orbits. Some pass through the inner Kuiper Belt at their closest approach to the Sun, but their elongated orbits take them far, far beyond. They can range outward to hundreds of astronomical units. Objects in the scattered disk were not born there. They were scattered by Neptune, thrown onto their current wild orbits by gravitational interactions during the period of Neptune's migration and in the billions of years since. The scattered disk is not a stable place. Objects there continue to be perturbed by Neptune every time they pass close to its orbit. Over long time scales, scattered disk objects can end up anywhere, thrown inward to become Jupiter family comets, thrown outward into the Oort cloud, or occasionally settled into more stable orbits in the classical belt. The scattered disk is the Kuiper Belt's chaotic underbelly, the population that never stopped moving. And then there are the detached objects. Objects like Sedna. Sedna is one of the most isolated objects ever found in the solar system. It was discovered in 2003 and has been studied intensively ever since, in part because its orbit makes almost no sense. Sedna's closest approach to the Sun is about 76 astronomical units, well beyond the outer edge of the main Kuiper Belt. Its farthest point from the Sun is somewhere around 937 astronomical units. At that distance, it takes 10,500 years to complete a single orbit. Sedna's orbit never comes close to Neptune, never comes close to any known planet. There is no known gravitational influence in the solar system that could have put Sedna where it is. This is the problem. The scattered disk objects have their unusual orbits because of Neptune. Neptune scattered them. But Neptune's reach only extends so far. Neptune can significantly perturb objects within roughly 100 astronomical units. Sedna's closest approach of 76 astronomical units is within that range. But the shape of Sedna's orbit, its extreme elongation, doesn't match what Neptune's scattering alone would produce. Something else moved Sedna. The most widely accepted explanation involves something that isn't there anymore. In the early solar system, the Sun almost certainly had stellar siblings. Stars that formed in the same molecular cloud as the Sun clustered together in a loose association before they drifted apart over millions of years. When those stars were still nearby, their gravity could have perturbed objects in the outer solar system, pulling them into the distant orbits we see today. Sedna may be a relic of that time, an object nudged by the gravity of a star that no longer exists anywhere near us. Its orbit preserves a memory of the Sun's early stellar environment, a record of company the Sun kept 4.5 billion years ago, before the cluster dispersed and the Sun was left alone. There's another explanation that gets a lot of attention. Planet 9. The evidence is circumstantial but persistent. Multiple objects in the outer solar system, Sedna included, have orbits that cluster together in ways that appear non-random. The orbital planes, the points of closest approach to the Sun, the shapes of the orbits, they align in a pattern. Statistical analyses of the known population suggest there is roughly a 1 in a few hundred chance that this clustering is random. That's not a definitive proof of anything. But it's compelling enough that two astronomers, Konstantin Batygin and Mike Brown of Caltech, published a paper in 2016, arguing that the most likely explanation is a large undiscovered planet in the outer solar system. Planet 9, as it's been called, would have roughly 5 to 10 times the mass of Earth. It would orbit the Sun at several hundred to 1,000 astronomical units, and it would take somewhere between 10,000 and 20,000 years to complete one orbit. It would be dim, extremely dim. At that distance from the Sun, it would reflect almost no light, which is why we haven't found it, despite years of searching. Or it doesn't exist. Some astronomers argue the clustering in the outer Kuiper Belt is a selection bias. We've been looking for these distant objects primarily in certain parts of the sky, and we're seeing clustering because of that, not because there's something causing it. A paper from 2021 examined the statistical evidence more carefully and found that when you account for observational biases, the clustering becomes less significant. Maybe not significant enough to require a 9th planet. The debate is ongoing. No definitive detection has been made. But every few years, new objects are found that either strengthen or complicate the pattern. If Planet 9 exists, it would reshape our understanding of the solar system's history. A world 5 to 10 times Earth's mass would be a significant addition to the planet count. Its gravitational influence would have been shaping the outer solar system for billions of years. It could be responsible for the orbits of Sedna and the other detached objects. It could explain other anomalies in the outer solar system that don't have obvious explanations. If it doesn't exist, we need another explanation for Sedna's orbit. And that explanation brings us back to the early stellar cluster, to the possibility that our solar system's outer architecture was shaped by stars that have long since drifted away. Either way, the outer solar system is telling us something we don't fully understand yet. And the question of whether something massive is lurking in the far outer solar system is one of the genuinely unresolved questions in planetary science. An answer we may have to wait decades to find. Back to something more immediate. Most of the comets that cross Earth's orbit right now came from the Kuiper Belt. Short-period comets, those with orbital periods of less than 200 years, are generally Kuiper Belt objects that got disturbed. Scattered by a gravitational nudge from Neptune or another large object into an orbit that dips into the inner solar system. Halley's Comet is the most famous example. Its orbital period is about 75 to 76 years. It has been observed and recorded by humans for over 2,000 years. The Chinese recorded it in 240 BC. Babylonian astronomers tracked it in 164 BC. Edmund Halley, in the early 1700s, was the first person to recognize that the comets observed in 1531, 1607, and 1682 were actually the same object returning on a predictable cycle. He predicted it would return in 1758. It did. More than 50 years after he made the prediction, and 16 years after he passed. Halley's comet is a piece of the Kuiper Belt that found its way inward. Every appearance throughout history, every comet that made ancient people look up in awe, was a frozen object from the outer solar system that got nudged onto a different path at some point in the geological past. The comets themselves are remarkable objects. A typical comet nucleus is a few miles to tens of miles across, irregular in shape, dark on the surface because organic compounds and carbon-rich material accumulate there, absorbing sunlight. Underneath that dark crust, the nucleus is mostly ice. Water ice, carbon dioxide ice, carbon monoxide ice, methane ice, mixed with rock and dust in varying proportions. This composition isn't uniform. Comets from different parts of the Kuiper Belt formed in slightly different conditions and have different chemical signatures. Studying the specific ratios of different ices in a comet's coma gives astronomers information about where in the original solar nebula the object formed. When a comet approaches the Sun, something dramatic happens. The surface temperature rises. The ices begin to sublimate. They don't melt because there's no atmospheric pressure to allow liquid water to exist. They go directly from solid to gas. This process releases material from the nucleus in jets. Jets of gas and dust streaming outward from specific hotspots on the comet's surface where ices are particularly concentrated near the surface. These jets are not gentle. They accelerate material off the nucleus at high speed. And because the nucleus has almost no gravity, that material escapes into space entirely, forming the coma, the fuzzy envelope of gas and dust that surrounds the nucleus as it nears the Sun. The solar, wind, and radiation pressure then push the coma material outward in two distinct tails. The ion tail, made of ionized gas, always points directly away from the Sun because it's blown by the solar wind. The dust tail, made of larger particles, curves gently along the comet's orbital path because those heavier particles take longer to respond to radiation pressure. A comet with both tails fully developed is one of the most beautiful objects visible in the night sky. And it's made entirely of material from the outer solar system, briefly illuminated by sunlight it hasn't seen in decades or centuries. Every time a comet passes through the inner solar system, it loses some of itself. Material is boiled off and lost to space. A typical short-period comet can only make a few thousand passes around the Sun before it has exhausted its volatile material and becomes an inert, dark, dust-covered lump of rock, indistinguishable from an asteroid. Some comets don't even make it that far. They break apart. The gravitational stresses of approaching the Sun, combined with the pressure of sublimating gases from within, can fracture a nucleus. Comet Shoemaker-Levy, 9, broke into at least 21 fragments before crashing into Jupiter in 1994. We watched it happen. 21 separate impact events over 6 days, each one leaving a dark scar in Jupiter's atmosphere larger than Earth. The fragments hit in sequence, following each other along the same orbital path, each impact adding another bruise to a band of Jupiter's atmosphere that stayed visible for months. Jupiter absorbs a lot of cometry and asteroid impacts. Its massive gravity attracts objects that might otherwise continue on into the inner solar system. Some models of solar system dynamics suggest Jupiter may have intercepted dozens of objects over the last 4.5 billion years that were originally on trajectories to hit Earth. Whether that makes Jupiter a guardian is a matter of ongoing debate. It also flings some objects inward that might otherwise have stayed in the outer solar system. The relationship is complicated. Jupiter is not protecting us so much as being enormous and nearby, and thereby changing the trajectories of things that would otherwise have had different fates. The surface environment of a typical Kuiper Belt object is something that deserves more attention than it usually gets. The temperature out there sits between about -340 degrees Fahrenheit and -380 degrees Fahrenheit, or roughly -207 to -229 degrees Celsius, depending on the object's distance from the Sun and how reflective its surface is. At those temperatures, most substances that are gases or liquids in everyday life are frozen solid. Nitrogen, which makes up 78% of Earth's atmosphere, is a solid on Pluto's surface. Methane, the main component of natural gas here on Earth, is a solid ice on Makemake and Eris. Carbon monoxide, a toxic gas at room temperature, is a surface frost on some Kuiper Belt objects. Carbon dioxide freezes solid at about -109 degrees Fahrenheit or -78 degrees Celsius. At Kuiper Belt temperatures, it has been a solid for 4.5 billion years. Water ice, the most familiar ice to us, is so cold out there that it behaves more like rock than like the ice in your freezer. Water ice at -350 degrees Fahrenheit, or about -212 degrees Celsius, has a compressive strength similar to granite. The mountains on Pluto are not fragile. They're harder than concrete. This has strange implications for the surfaces of these worlds. We think of ice as slippery, unstable, prone to melting. The ice on Kuiper Belt objects is none of those things. It is a structural material, a building material. Mountains of water ice on Pluto stand as tall as major mountain ranges on Earth because the ice is cold enough and hard enough to support that height against gravity without flowing or collapsing. The chemistry of these surfaces is stranger still. When cosmic rays and ultraviolet light from the sun hit ices containing carbon, hydrogen, nitrogen, and oxygen, they drive chemical reactions. Organic molecules form, complex ones. Molecules with carbon-carbon bonds, carbon-nitrogen bonds, long chains and ring structures. Astronomers call this material tholins. It's a reddish-brown gunk that forms on the surface of many Kuiper Belt objects when radiation processes ices over long timescales. Millions of years of irradiation, slowly transforming the original pristine ices into something much more complex. The reddish color of some Kuiper Belt objects and many comets comes from this material. Tholins are interesting for a reason that goes beyond chemistry. Similar processes involving ultraviolet light and ices rich in carbon and nitrogen may have been how some of the prebiotic molecules, the building blocks of life, were first assembled. Not on Earth. Out here, in the cold outer solar system. Laboratory experiments have shown that when you irradiate mixtures of ice that resemble the compositions found on Kuiper Belt objects, you produce amino acids. You produce sugars. You produce nucleobases, the molecules that are the building blocks of RNA and DNA. Not all of them, not in large quantities, but the chemistry works. The outer solar system is not just a cold, inert place. It is a slow chemical laboratory, driven by radiation rather than heat, assembling complexity out of simplicity over billions of years. Some of that material was delivered to the early Earth by comets. When comets hit the early Earth during the heavy bombardment period, they brought with them water, carbon dioxide, nitrogen, and a suite of organic molecules. The amino acids found in some meteorites, including ones derived from cometary material, are exactly the kinds of molecules tholins can produce. Multiple amino acids have been found in cometary material and in carbonaceous meteorites. Not one or two, multiple. The Kuiper Belt may have contributed some of the chemical starter kit for life on Earth. That is a claim that should land heavily. We are partly made of material that came from the outer solar system. The chemistry that began the process that eventually, over billions of years, led to cells, then multicellular organisms, then you, may have been assembled in the cold dark beyond Neptune and then delivered here. The New Horizons mission was humanity's first deliberate visit to the Kuiper Belt. The spacecraft launched in January of 2006, the fastest spacecraft ever launched at the time, leaving Earth at a speed of about 36,000 miles per hour relative to the Sun. It was aimed at Pluto, a target 9 years and more than 3 billion miles away. On July 14, 2015, New Horizons flew past Pluto at a distance of about 7,800 miles. It was traveling at about 30,000 miles per hour relative to Pluto. The flyby lasted a matter of minutes. New Horizons had to operate autonomously during the flyby because the communication delay between Pluto and Earth was about 4 hours and 25 minutes at the time. You couldn't send a command and have it arrive in time to matter. The spacecraft had to make its own decisions, execute pre-programmed sequences, and hope everything worked. Everything worked. The images came back over the following months because New Horizons' radio transmitter operates at only about 15 watts, roughly the power of a dim light bulb, and it takes that signal more than 4 hours to reach Earth, even traveling at the speed of light. Downloading the entire dataset took 16 months. 16 months. The closest flyby of a new world in planetary history. And it took over a year just to receive all the data because physics is uncompromising about how fast electromagnetic signals travel. Then, in January of 2019, New Horizons executed a second flyby, this time of a much smaller, more distant, and more primitive object, Arrokoth. Arrokoth sits about 44 astronomical units from the Sun. It's a contact binary, 2 lobes fused together into a shape that looks roughly like a snowman. The larger lobe is nicknamed Ultima. The smaller one is nicknamed Thule. The way they're connected matters. Most large objects in the solar system formed through chaotic collisions. High-speed impacts. Bodies smashing into each other and merging or shattering. Arrokoth is different. The 2 lobes appear to have come together gently, slowly, orbiting each other at very low relative speed before gradually drifting together and touching. A process called accretion by mutual orbit, or a cold merger. This gentleness is significant. It means Arrokoth formed in a relatively quiet environment, far from the gravitational turmoil that characterized the inner solar system, far from Jupiter's influence, far from the chaos of planetary migration. Arrokoth is thought to be among the most pristine objects ever studied. a direct sample of the material and processes that built the outer solar system 4.5 billion years ago. Its surface is covered in methanol ice and complex organic compounds. It is uniformly reddish, that same tholin coloration that radiation processing produces over billions of years. It has no obvious craters from major impacts, which tells us that even the Kuiper Belt, for all its population of objects, is sparse enough that Arakoth has spent 4.5 billion years out there without being significantly hit. Think about what that means. An object sitting in the outer solar system for 4.5 billion years, and the space around it is so empty that it hasn't been hit hard enough to leave a large crater. That fact alone tells you something about the true emptiness of the Kuiper Belt, even within its apparent density. Neptune's role in shaping the Kuiper Belt cannot be overstated. Neptune is the solar system's outer enforcer. At about 17 times Earth's mass, Neptune orbits at 30.1 astronomical units, right at the inner edge of the Kuiper Belt. Its gravity does not gently influence the objects near it. It dominates them. Any object that drifts too close to Neptune's orbit gets disturbed. The perturbation might be small, a tiny nudge over millions of years. But in a gravitational system, small nudges compound. An object's orbit that starts slightly elliptical can, over millions of years of repeated gravitational interactions with Neptune, become significantly more elliptical. Eventually, that object's orbit crosses Neptune's own orbit. And then, Neptune's gravity affects it more strongly, and the process accelerates. This is called orbital instability, and it clears a region just outside Neptune's orbit. Between about 30 and 35 astronomical units, the Kuiper Belt is significantly depleted. This is not where most Kuiper Belt objects are found. Any object that wanders into that zone gets scattered, kicked outward into the main belt, kicked inward toward the Sun to become a comet, or kicked to a highly elliptical orbit in the scattered disk. The main classical Kuiper Belt, the stable region between 42 and 48 astronomical units, sits safely outside Neptune's direct influence. But even there, Neptune reaches through the resonances it maintains with objects like Pluto, keeping a gravitational hand in the population dynamics, even at those distances. The stability of the classical Kuiper Belt is not permanent. On very long timescales, billions of years, even the classical belt will slowly erode. Objects that drift slightly into unstable orbits will be scattered. The overall population will slowly decline, not within any human-relevant timeframe. The Kuiper Belt of 1 billion years from now will look almost identical to what it looks like today. But on timescales comparable to the age of the solar system itself, things change. The outer solar system, which looks frozen in time, is in slow motion. There is a specific part of the Kuiper Belt story that most people have never heard, and it is one of the most dramatic things that happened in our solar system. It happened roughly 3.9 billion years ago. For the first 500 million years or so after the planets formed, the outer solar system was in a different configuration than it is today. Jupiter, Saturn, Uranus, and Neptune orbited somewhat closer to the Sun. They were packed more tightly together, and they were surrounded by an enormously more massive version of the Kuiper Belt, a vast disk of small, icy bodies containing perhaps tens of Earth masses of material. For a while, this configuration was stable. The planets moved in their orbits. The disk remained in its place, a kind of equilibrium. Then, something changed. Jupiter and Saturn gradually drifted into a 2-to-1 orbital resonance with each other. For every orbit Saturn completed, Jupiter completed exactly 2. When two massive planets lock into resonance, their gravitational influences amplify each other at specific points in their orbits. Instead of nudges that mostly cancel out over time, the nudges started adding up in the same direction. The resonance destabilized the outer solar system. Saturn began to migrate outward. As it did, it pulled Uranus and Neptune outward with it. Uranus and Neptune passed each other. Their mutual gravitational interactions threw them into new orbits, and Neptune, pushed outward by the cascade of interactions, plunged into the primordial Kuiper Belt like a wrecking ball. The effect was catastrophic. Neptune's passage through the dense outer disk scattered objects in every direction. Some were launched into the inner solar system. They rained down on the terrestrial planets: Mercury, Venus, Earth, the Moon. The Moon's surface preserves this history in its craters. This event is called the Late Heavy Bombardment. The period between about 3.9 and 3.8 billion years ago, when the inner solar system was pummeled by impacting bodies at a rate dramatically higher than it had been before. The evidence for the Late Heavy Bombardment comes primarily from lunar samples returned by the Apollo missions. When you date the rocks from the lunar highlands, a significant cluster of ages falls around 3.9 billion years. Objects from many different parts of the Moon's surface all show evidence of melting, recrystallization, and impact around the same time. That cluster, that tight grouping of ages, suggests a pulse of impacting material, not a gradual decline. Something triggered a spike of bombardment at roughly 3.9 billion years ago. Neptune's migration through the Kuiper Belt is the best explanation we have. The model that captures this event is called the Nice model, named after the city in France where it was developed. It was published in 2005 and immediately became one of the most influential ideas in planetary science in decades. It explained not just the late heavy bombardment, but also the current orbital positions of the giant planets, the distribution of Jupiter Trojans and other resonant asteroid groups, and the overall structure of the Kuiper Belt. It explained too much, in a sense. A model that explains that many different observations from first principles is usually pointing at something real. Here on Earth, 3.9 billion years ago, corresponds to a period very early in the story of life. The earliest definitive evidence for microbial life on Earth dates to somewhere around 3.5 billion years ago. Some chemical evidence suggests life may have appeared even earlier, perhaps 3.7 or 3.8 billion years ago. If life existed during the late heavy bombardment, the impacts would have been severe. Some models suggest that the largest impacts during this period may have briefly vaporized Earth's oceans. If life existed in shallow waters or at the surface, it would not have survived those events. But life in deep ocean hydrothermal vents might have. The rock above would have shielded the vents from impact effects. The heat would have continued flowing up from Earth's interior, regardless of what was happening on the surface. Life, if it existed at all during the bombardment, would have had to weather an extraordinary period. The solar system was throwing everything it had at Earth. And then it stopped. Because Neptune had finished its outward migration. Because the Kuiper Belt had been depleted of most of its original material. Because the late heavy bombardment had exhausted the supply of projectiles. What remained after all of that was a quieter solar system, the one we live in today. And the Kuiper Belt we see now is the remnant of that devastation. Less than a tenth of the primordial outer disk, survivors of the chaos. A hollowed-out ghost of what was once out there. Every Kuiper Belt object you could name, Pluto, Eris, Makemake, Haumea, Arakoth, every one of them is here because it found an orbit stable enough to survive that period. The ones that didn't are long gone, crashed into Jupiter, crashed into Earth, ejected into interstellar space, dissolved into comets that made a few passes around the Sun and then gave themselves away piece by piece. Meteor showers mark the Kuiper Belt's presence in our sky more visibly than almost anything else. When Earth crosses the path of debris left behind by a comet, the small particles of rock and ice enter our atmosphere at high speed and burn up, producing streaks of light. Meteor showers. The Perseid shower, which peaks every August, comes from comet Swift-Tuttle, a Kuiper Belt object in a long elliptical orbit with a period of about 130 years. The debris stream Swift-Tuttle has deposited along its orbital path is broad enough that Earth takes several days to pass through it. At the peak of the shower, you can see dozens of meteors per hour from a dark location, each one a grain of Kuiper Belt material, burning up in Earth's atmosphere at speeds of about 37 miles per second. The Leonid shower every November comes from Comet Tempel-Tuttle, another periodic comet with a roughly 33-year period. Most years, the Leonids produce a moderate shower. But in years when the comet has passed through the inner solar system recently, the debris stream is much denser. In 1833, observers reported Leonid rates of over 100,000 meteors per hour. The sky was reportedly full of streaks of light. People who didn't know what was happening thought the world was ending. It wasn't. It was just the Kuiper Belt visiting. The Geminid shower in December is unusual because it comes not from an active comet, but from an asteroid-like object called 3200 Phaethon. Phaethon is thought to be an extinct comet nucleus, an object that has depleted most of its volatile material and now looks like a dark asteroid, but that still has enough residual material to produce a debris stream. The Geminids are notable for being one of the most reliable and most active meteor showers of the year, producing 80 to 120 meteors per hour at peak. The meteor showers have names and dates on our calendars because Earth crosses the orbital paths of Kuiper Belt objects every year. The sky that ancient people watched is partly the Kuiper Belt announcing itself. There is one more aspect of the Kuiper Belt that has been growing in scientific importance. It involves what the Kuiper Belt can tell us about other solar systems. When astronomers observe young stars, they frequently detect disks of material around them, protoplanetary disks, the structures from which planets and Kuiper Belt analogues are forming. What's striking is that many of these disks around other stars are far more massive than our own Kuiper Belt, far more densely populated, far more extensive. Some young stars have debris disks that contain the equivalent of hundreds of Earth masses in small bodies. Our Kuiper Belt contains, in total, perhaps a tenth of an Earth mass. This is not because our solar system is unusual. We think we're simply looking at those other disks early, before their own equivalent of Neptune's migration has happened, before their own late heavy bombardment has swept through and depleted the primordial population. If that interpretation is correct, all those rich, massive debris disks around other stars are destined to be depleted. Chaotic planetary migrations will happen. Giant planets will scatter their outer disks. The bombardment will occur. And what will remain will be a quiet, sparse remnant like our own Kuiper Belt. Which means solar systems that have gone through this process, that have mature Kuiper Belts, that look like ours, may be solar systems that have completed a necessary step. The chaos was necessary. The violence was part of the process. The sweeping and scattering and bombardment that shaped the Kuiper Belt into what it is today may be an essential stage in making an inner solar system habitable. A massive, primordial outer disk is a threat to inner planets. It's a reservoir of impactors waiting for a trigger. The late heavy bombardment was brutal, but it was also finite. It happened once, and then it was over. Without Neptune's migration through the outer disk, without the dispersal of that original population, the bombardment might have been ongoing. A constant stream of impacting material, never letting up, never giving biology time to establish itself. The Kuiper Belt we have now, depleted and sparse, is actually the solar system's outer disk in its safe configuration, swept clean enough to not be a constant threat to Earth. That process, migration, sweeping, dispersal, is something we now observe signatures of around dozens of other star systems. Warm debris disks whose dust signatures change over time. Stars whose outer regions brighten and dim in ways consistent with collisions and dispersals. We are watching other solar systems go through what ours went through. And in those observations, the Kuiper Belt stops being just a distant, cold place at the edge of our solar system. It becomes a data point in a much larger question. One example of a process that may be universal. A step that solar systems take on the way to something like stability. Stable enough, for long enough, for life to get started. 2 spacecraft are currently moving away from the Sun and have already passed through the Kuiper Belt. Voyager 1 and Voyager 2, both launched in 1977, are still operating and transmitting data nearly 5 decades later. Voyager 1 is currently the most distant human-made object ever created. As of 2026, it sits at more than 170 astronomical units from the Sun. It crossed the heliopause, the boundary where the solar wind gives way to interstellar space, in 2012. It is in interstellar space now. Voyager 2 crossed the heliopause in 2018. It is currently at about 144 astronomical units. Neither spacecraft is in the Kuiper Belt. They passed through the region years ago. They're well beyond it now, in the space between the Sun's heliosphere and the true boundary of the Oort cloud. New Horizons, after its flyby of Arrokoth in 2019, has continued outward. It is the only spacecraft designed specifically to study the Kuiper Belt, and it will continue operating until its nuclear power source degrades too much to sustain instruments, probably sometime in the late 2030s. If a suitable target can be identified and funding approved, another Kuiper Belt object flyby is possible before then. The challenge is finding the target. New Horizons is moving in a specific direction. It can't change course significantly. Finding a Kuiper Belt object that happens to lie along or near that narrow trajectory requires enormous telescopic surveys of a small patch of sky, looking for faint, slow-moving objects against a dense stellar background. When New Horizons was searching for a post-Pluto target, scientists used the Hubble Space Telescope to conduct an intensive survey. It took extensive observation time before Arrokoth was found in a suitable position. Any additional target will require a similar or more intensive search. The Kuiper Belt, for all its hundreds of thousands of members, is hard to find in the sky when you're looking for one specific object that happens to be in the right position. Telescopes like the Vera C. Rubin Observatory, which began science operations recently, may change this. It is designed to survey the entire visible sky repeatedly, building up a census of faint solar system objects that will be orders of magnitude larger than anything we've had before. Over 10 years of operations, Rubin is expected to discover tens of thousands of new Kuiper Belt objects, including many in the distant scattered disk and extended scattered disk, where the orbital statistics may finally settle the question of Planet 9. The Rubin Observatory will also be able to track how the discovered objects move across the sky with high precision, allowing their orbits to be calculated. With tens of thousands of new outer solar system objects, the patterns in their orbital distributions will either clearly show the signature of a massive perturbing planet or clearly show that no such signature exists. One way or another, within the next decade or so, we should have an answer. Either the solar system has a ninth planet we've never seen, or the orbital clustering that suggested it is a statistical artifact. Both outcomes reshape how we understand the outer solar system. Here is what the Kuiper Belt actually is, stripped of all the technical language. It is a record. It is the most complete record of the solar system's violent past that exists. Every frozen world out there carries in its composition, its orbit, its shape, its surface chemistry, information about what the early solar system was like, about where it formed, about what hit it, about how the giant planets moved and where they migrated and what they swept through. The dwarf planets carry records we haven't fully decoded yet. Their internal structures preserve temperature and pressure histories from their formation. Their surface modifications from radiation and rare impacts mark the passage of billions of years. The rings around Haumea record a collision from the deep past. The Haumea family records that same collision in the orbits of scattered debris. The cold classical Kuiper Belt binaries record the gentle accretion conditions of the outer solar nebula before Neptune arrived. The orbital architecture of the Kuiper Belt, the resonances and gaps and clustering of the scattered objects, is a direct imprint of the giant planet's dynamical history. It's a transcript of what happened. And we're only now beginning to read it properly. The comets that cross Earth's sky came from there. The meteor showers, you know by name, came from there. The water you drink may have been delivered to early Earth by objects from there. The organic molecules that were part of life's starting chemistry may have been synthesized there and delivered by impact. The Kuiper Belt is not remote. It is not separate from us. It is connected to everything that made this planet habitable. The bombardment it supplied to the early Earth may have delivered the raw materials that life needed. The subsequent clearing of the bombardment gave life the time and stability to take hold. The comets it continues to send into the inner solar system leave their debris in Earth's path, producing meteor showers that ancient humans watched and named and built mythology around. We are partly made of material from the outer solar system. The atoms in your body include oxygen and carbon and nitrogen that arrived here billions of years ago in icy bodies from beyond Neptune. That is what the Kuiper Belt is, not a distant, empty, irrelevant region. A place deeply entangled with the history of everything alive on Earth. There are worlds out there we have never seen. Objects larger than Pluto that we suspect exist but haven't confirmed. Entire classes of bodies with chemical compositions we haven't yet sampled. Orbital families that preserve records of collisions we haven't yet decoded. And beyond the Kuiper Belt, in the extended scattered disk and the detached objects, there may be answers to questions we don't even know how to ask yet. Whether there is a ninth planet. Whether the Sun passed close to another star in its early history. leaving that gravitational signature in Sedna's impossible orbit. Whether the structure of the outer solar system is unique to us or common across the galaxy, these are not small questions. They are questions about the history of the solar system as a whole, about whether what happened here, the migration of giant planets, the violent sweeping of the outer disk, the late heavy bombardment, the eventual quieting, was a fluke or a pattern. If it's a pattern, then Kuiper belts around other stars may be markers of something important. Signatures of solar systems that went through their violence and came out the other side. Systems where the inner planets had time to stabilize. Where liquid water could persist on surfaces. Where life had a chance. If that's right, then looking for Kuiper belt analogues around other stars is not just an academic exercise in planetary science. It's part of the search for whether we are alone. Actually, let's step back and look at something that rarely gets the attention it deserves. The Kuiper belt has a boundary problem. On one side, it's bounded by Neptune's gravitational reach. Objects that get too close to Neptune's orbit get scattered away. That's the inner boundary, somewhere around 30 to 35 astronomical units. But the outer boundary is less clear. The classical Kuiper belt fades out around 50 astronomical units. Beyond that, the number of detected objects drops sharply. This drop is sometimes called the Kuiper cliff, and astronomers don't fully agree on why it's there. One possibility is that the Kuiper belt simply thins out naturally at that distance because there was less material in the original disk that far from the Sun. The density of the solar nebula fell off with distance, so fewer objects formed out there. Another possibility is that something cleared the region beyond 50 astronomical units. A passing star, an early planetary body, or Planet 9 itself, if it exists. The Kuiper cliff is one of those features that looks straightforward from a distance and gets more puzzling the closer you examine it. A sharp drop in the number of objects at a specific distance, with no obvious single cause. Every attempt to model the outer solar system has to account for it. Every proposed explanation for the Kuiper belt's overall structure has to explain why objects seem to thin out so sharply at 50 astronomical units while still leaving behind the scattered disk. Objects with orbits that extend far beyond. There is also the question of what the Kuiper belt looks like from the outside. If an alien civilization with a sufficiently advanced telescope pointed it at our solar system, they would see it as a star with a debris disk. They would measure properties of that disk, its extent, its dust, luminosity, its temperature, and from those measurements, they would try to infer what kind of solar system we have. They might conclude we have a cold, sparse debris disk characteristic of a mature solar system that has already gone through its planetesimal clearing phase. They would not see individual Kuiper belt objects. They would see the collective glow of dust produced by occasional collisions between them. This is exactly how we observe other solar systems. We detect their debris disks through infrared emission. Dust grains warmed slightly by starlight glow in the infrared, and that glow is detectable even from many light years away. Several nearby stars have debris disks that astronomers study in detail. Epsilon Eridani is one, a star about 10.5 light-years away. It has a debris disk at roughly 35 to 60 astronomical units, similar in extent to our Kuiper belt. It also appears to have additional structure, possibly rings or gaps, that might indicate planets shaping the disk much as Neptune shapes ours. Fomalhaut is another, about 25 light-years away. It has an unusually sharp, narrow ring of debris at roughly 140 astronomical units. The sharpness of the ring suggests it's being confined by the gravity of one or more planets orbiting near it. Hubble Space Telescope. Observations in 2008 appeared to show a point source moving along an orbit within the disk, tentatively identified as a planet. Later, observations complicated the interpretation. The story is still unfolding. Beta Pictoris is younger than the Sun, about 23 million years old. It has a massive, warped debris disk extending hundreds of astronomical units from the star. The disk is warped because a planet, Beta Pictoris b, orbits within it and gravitationally tilts the inner regions. What we're seeing in these other systems are Kuiper Belt analogues at different stages of evolution. Fomalhaut's disk might be what ours looked like a billion years ago. Epsilon Eridanes might be what ours looks like to outside observers now. Beta Pictoris is what ours looked like when the Sun was young, before the planets migrated and before the late heavy bombardment cleared most of the material away. Our own Kuiper Belt is one frame in a long movie. And by watching other solar systems at different stages of that same movie, we can reconstruct what the whole film looks like. Something that comes up surprisingly rarely in discussions of the Kuiper Belt is the question of what it's actually like to be out there. Not as an observer looking from Earth, but as something hypothetically present in the Kuiper Belt itself. At 40 astronomical units from the Sun is still there, still visible, but it looks nothing like the Sun you see from Earth. From Earth, the Sun has an apparent angular diameter of about half a degree. It fills a visible disk in the sky. You can't look at it directly. It illuminates everything around you with blinding intensity. From 40 astronomical units, the Sun's apparent angular diameter is about 44 arc-seconds, about 80% smaller than what we see from Earth. From that distance, the Sun still looks like a disk to a careful observer, but just barely. It's about 1,600 times dimmer than we see it. What you'd perceive as an observer is a very bright star. Not a star that warms your face. Not a star that floods your surroundings with light. A very bright star. The brightest object in the sky by far. But a star. Something you could look at, briefly, with your eyes. The surface of a Kuiper Belt object lit by that light would be in deep twilight. Not the complete darkness of deep space. Not the bright daylight of Earth's surface. Something in between. Like the light level just after the Sun has set on an overcast evening. Enough to see by, but not enough to illuminate with any warmth. And the warmth. At 40 astronomical units, the energy reaching a surface from the Sun is about 1,600 times less than at Earth. The temperature of a surface in equilibrium with that light depends on how reflective the surface is. A dark surface absorbs more light and reaches a slightly higher temperature. A bright surface reflects more light and stays colder. For a typical Kuiper Belt object with moderate reflectivity, surface temperatures fall in the range of -340 to -370 degrees Fahrenheit, or about -207 to -223 degrees Celsius. That is close to the lowest naturally occurring temperatures anywhere in the solar system. Lower than the surface of Pluto on its dark side. Lower than the permanently shadowed craters near the lunar poles, where temperatures reach -400 degrees Fahrenheit, or about -240 degrees Celsius. Some of the coldest measured surfaces in the inner solar system. At those temperatures, chemistry essentially stops. Molecular motion becomes so sluggish that reactions that would happen in an instant at room temperature would take millions or billions of years at Kuiper Belt surface temperatures, which is why the surfaces of Kuiper Belt objects are time capsules. The chemistry that happened when they formed, the original composition of the solar nebula at those distances, is preserved because there's not enough energy to change it. The only processes altering the surfaces are radiation damage from cosmic rays and the slow accumulation of tholins, which happen on timescales of millions of years. These are the slowest worlds in the solar system, the most preserved, the most ancient. And in that preservation is information. Every measured absorption feature in the spectrum of a Kuiper Belt object's surface tells us what molecules are present. Every ratio of one ice to another tells us about the temperature and pressure conditions where the object formed. Every gradient in surface composition from one hemisphere to another tells us about how radiation modifies the surface over time. Reading those spectra is like reading geological strata. Each layer of information records a different chapter of the object's history, and the chapters go back 4.5 billion years. The process by which Kuiper Belt objects form is itself fascinating and not fully understood. We know they formed by accretion, small particles sticking together to make larger ones. But the details of how you get from small particles to large bodies is a problem that planetary scientists have been working on for decades. The challenge is what's sometimes called the meteor barrier. When particles are very small, smaller than roughly a centimeter, they collide gently and stick together. Electrostatic forces, weak chemical bonds, and the fluffy structure of dust aggregates all help small particles grow. But as particles grow larger, collisions become more violent. At some size, collisions start destroying objects rather than growing them. A centimeter-sized pebble hitting another centimeter-sized pebble at high speed doesn't produce a larger object. It produces fragments. And large objects, kilometers in size, grow relatively efficiently through gravity. Their mass is enough to attract smaller particles and hold them. The problem is the transition zone, the range of sizes between a few centimeters and a few kilometers. How did objects cross that gap? One answer involves streaming instabilities. In the disk of material around the young sun, gas drag caused small particles to drift inward toward the sun. But in regions where the particle concentration was slightly higher than average, the particles and gas interacted in a way that amplified the concentration. Particles got drawn into dense clumps. And those clumps, dense enough and massive enough, could collapse under their own gravity, forming kilometer-sized bodies almost directly from centimeter-sized pebbles. This process, gravitational collapse through streaming instability, could explain how the building blocks of the Kuiper Belt formed quickly before they had time to be destroyed by collisions. And crucially, streaming instability tends to form objects with a characteristic size. Bodies of roughly 100 kilometers across. Not a power law distribution of sizes from tiny to huge. A preferred size. Observations of the Kuiper Belt population seem to be consistent with this. There's a break in the size distribution around 100 kilometers, where the slope changes, possibly reflecting the imprint of the formation process. Arakoth, with its cold merger of two similar-sized lobes, fits naturally into this picture. 200-kilometer-class objects, formed by streaming instability in the same region of the disk, slowly drawn together by gravity over millions of years, gently touching. It's a beautiful story. A perfectly peaceful origin for one of the most pristine objects we've ever visited. Two piles of ancient solar nebula drifting together so slowly that the collision left no damage. The violence came later. Neptune arrived, and everything changed. One thing the Kuiper Belt does that most people never consider is generate dust. Kuiper Belt objects collide. Not often. The belt is sparse enough that major collisions are rare on human timescales. But over millions and billions of years, objects do hit each other. And when they do, they produce fragments. Smaller objects. And those smaller objects produce smaller collisions. And so on, down to dust. This dust is called Kuiper Belt dust. It's different from the dust produced by asteroid belt collisions. It's colder. It formed from different materials, and it's distributed throughout the outer solar system. Kuiper Belt dust drifts inward, toward the sun, under the influence of radiation pressure and a subtle effect called the Poynting-Robertson effect. Sunlight hits dust particles slightly on one side as they orbit the sun, and the momentum of the absorbed and re-emitted photons causes the particles to very slowly spiral inward. Very slowly by human standards. Rapidly by geological standards. A dust grain from the Kuiper Belt will spiral into the inner solar system over millions of years. Some of this dust ends up in Earth's atmosphere. We collect interplanetary dust particles in the stratosphere, using high-altitude aircraft and balloons to catch particles before they settle. Some of those particles have compositions consistent with outer solar system origins. Pieces of the Kuiper Belt, fallen to Earth, smaller than a human hair, now sitting in collection chambers in laboratories. The Kuiper Belt is literally raining on us. Not visibly, not noticeably. But the outer solar system reaches us in dust, as well as in comets and meteor showers. The question of water deserves its own discussion. Earth has an enormous amount of water, oceans covering 71% of the surface, ice at the poles, water in the atmosphere, water dissolved in rocks and minerals throughout the crust and mantle. Where did all of it come from? This question has been debated for decades. The early Earth, during its formation, was intensely hot. Molten rock, volcanic outgassing, temperatures high enough to evaporate oceans if any liquid water tried to form. Water that was incorporated into the growing Earth during accretion could have been driven off to space by the heat and by impacts. So some of Earth's water may have arrived later, after the planet cooled, delivered by impacting bodies from colder regions of the solar system. Comets, asteroids from the outer asteroid belt, and possibly objects from the Kuiper Belt itself. The evidence is complex. Comets contain enormous amounts of water ice. They are, in some sense, flying snowballs. When they hit a planet, they deliver water. But there's a complication. Water comes in different varieties based on isotope ratios. The ratio of deuterium, which is heavy hydrogen, to ordinary hydrogen in water is called the D to H ratio. Earth's oceans have a characteristic D to H ratio, and that ratio can be compared to the D to H ratio in different types of comets and asteroids. Comets from the Oort cloud, the long-period comets, have D to H ratios roughly twice as high as Earth's oceans. They don't match. Comets from the Jupiter family, which includes many Kuiper Belt objects that have migrated inward, have been measured more recently with spacecraft. The Rosetta mission measured the D/H ratio of Comet 67P, Churyumov-Gerasimenko, and found it was also much higher than Earth's ocean water. Carbonaceous chondrite asteroids from the outer asteroid belt have D/H ratios that match Earth's oceans much better. This suggests that most of Earth's water came from asteroid belt objects rather than from Kuiper Belt comets. But the story isn't simple. Different comets have different ratios. The population of Kuiper Belt objects is not uniform, and we've only measured a handful of comets precisely. The contribution of Kuiper Belt material to Earth's water remains an open and active research question. The answer matters because it tells us how much of Earth's key ingredient for life came from the outer solar system, and whether other planets in other solar systems might receive similar deliveries. There is something philosophically strange about the Kuiper Belt that doesn't come up in the scientific literature, but that matters. The Kuiper Belt is a record of failure. Not failure in the negative sense, but failure in the literal sense. The things in the Kuiper Belt are objects that failed to become planets. They tried. Accretion was happening. Material was clumping. Objects were growing. For hundreds of millions of years, the outer disk was on its way to building something. And then Neptune arrived, and the gravitational energy of a migrating giant planet overwhelmed the gentle processes that had been quietly assembling worlds. The Kuiper Belt is what's left after that process was interrupted. The survivors of a planet that was never allowed to form. Some scientists have estimated that if the Kuiper Belt had been left alone, if Neptune had never migrated through it, the material out there could have accumulated into a planet with a mass somewhere around Earth's mass, or possibly larger. A fifth terrestrial planet. In the far outer solar system. We don't have that planet. We have the Kuiper Belt instead. Every Kuiper Belt object is a fragment of that potential world. A small piece of something that could have been much larger. And in its fragmented state, in its billions of pieces spread across an enormous volume, it tells us more about the solar system's history than that potential planet ever could have. The failure was more informative than success would have been. The Kuiper Belt will outlast most of what we think of as permanent about the solar system. The Sun will not always be like it is today. About 5 billion years from now, the Sun will exhaust the hydrogen in its core. It will expand into a red giant, swelling outward to perhaps 150 times its current radius. Mercury will be engulfed. Venus will be engulfed. Earth may be engulfed, or may barely survive in a scorched, airless, oceanless state, depending on exactly how much mass the Sun loses in the process. As the Sun expands, the habitable zone moves outward. The region where liquid water can exist on a planetary surface shifts from where Earth currently sits to somewhere out near where Jupiter and Saturn are now. And beyond that, in the Kuiper Belt, the ice will melt. For the first time in 4.5 billion years, the Kuiper Belt objects will receive enough heat to undergo real change. The ices will sublimate. Nitrogen and methane will boil off entirely. Water will melt. The rocky cores of these objects, buried under all that ice for billions of years, will be exposed. Some Kuiper Belt objects may briefly have liquid water on their surfaces as the Sun's heat sweeps outward. If the chemistry of tholins and organic compounds sitting on those surfaces has any relevance to what we know about prebiotic chemistry, those moments of liquid water might be interesting in a biological sense. not likely to produce life on any relevant timescale. The Sun's red giant phase will last only about 1 billion years, and the conditions will be complicated. But the idea that the outer solar system may experience a brief warm period, its own moment of habitable zone chemistry, billions of years from now, is not something to dismiss entirely. After the red giant phase, the Sun will shed its outer layers as a planetary nebula. The core will remain as a white dwarf. About half the Sun's current mass, compressed into a volume roughly the size of Earth. The outer planets will likely survive. Uranus and Neptune will continue orbiting the white dwarf, and the Kuiper Belt, somewhat depleted by the red giant's heat and stellar wind, will also survive. Objects in the outer Kuiper Belt, the ones most distant from the Sun, will be the least affected by the red giant phase. They will still be there, orbiting a dim white dwarf, billions of years after the Sun has transformed. Frozen, dark, preserved. The most distant Kuiper Belt objects may be the longest-lasting relics of the original solar system formation, surviving the red giant, surviving the transition to white dwarf, orbiting quietly in the dark for billions of years after Earth is gone. The Kuiper Belt began before the planets. It will likely outlast them. The infrastructure of deep space astronomy is slowly being pointed more systematically at the outer solar system. The James Webb Space Telescope, launched in 2021 and fully operational since 2022, is capable of studying Kuiper Belt objects in unprecedented detail. Webb observes primarily in infrared light. At Kuiper Belt temperatures, objects radiate most of their thermal energy in the infrared. Webb can measure surface temperatures directly. It can detect specific molecular signatures in surface ices with a sensitivity far beyond any previous telescope. It can study the albedo, the reflectivity, of surfaces at multiple wavelengths, distinguishing between different types of ice and organic material. Webb has already been used to study trans-Neptunian objects. Observations in its first 2 years of operation have already revealed new details about the surface chemistry of objects in the Kuiper Belt and scattered disk, including measuring water ice directly on the surface of Arrokoth and confirming the presence of carbon dioxide and carbon monoxide ices on other objects. These observations are building up a chemical census of the outer solar system, a map of what's present and where. That will take years to fully interpret. The combination of Webb's sensitivity with the discovery power of Rubin's sky surveys means the next decade is likely to be one of the most productive in the history of Kuiper Belt research. More objects will be found. More of them will be characterized. The statistics of their orbital distributions will improve. And slowly, the picture of what happened in the outer solar system billions of years ago will come into focus. Not perfectly. Not completely. The outer solar system will remain one of the great frontiers of planetary science for the rest of this century, at minimum. But the fog is thinning. Each observation strips away a little more of the uncertainty. That is how science works out here. Slowly. Carefully. Building understanding from individual data points collected over years and decades. The Kuiper Belt also connects to one of the deepest questions in planetary science. What is a planet? The International Astronomical Union's definition from 2006 settled the question of Pluto's status, but it didn't really settle the underlying question. The definition requires that a planet has cleared the neighborhood around its orbit. But what does cleared mean exactly? How do you quantify it? One approach is to calculate what's called the orbital clearing parameter, sometimes labeled lambda. This is a measure of how much mass a body has swept up or scattered out of its orbital zone over the age of the solar system. Large planets have high values. Pluto has a value about 10,000 times smaller than the smallest recognized planet. By this measure, a planet is something that dominates its orbital zone, something whose gravity is the most important force affecting the motion of other objects in that region. Neptune dominates its orbital zone. That's why objects near Neptune's orbit get scattered, get locked into resonances, get pulled into the Kuiper Belt family structure. Neptune's gravity is the first-order influence on everything near it. Pluto does not dominate its orbital zone. Pluto shares its region with thousands of other Kuiper Belt objects. Its gravity has no detectable influence on the overall structure of the Kuiper Belt. Pluto is a passenger in the Kuiper Belt, not a driver. This distinction, passenger versus driver, captures something real about the difference between planets and smaller bodies. But there's a deeper question hiding in this. How did the planets come to dominate their orbital zones in the first place? By growing large enough, through accretion, to scatter or absorb everything around them. Neptune grew large enough. The Kuiper Belt objects didn't. The Kuiper Belt is the graveyard of bodies that were on the way to planehood when the process was interrupted. So the question of what a planet is connects directly to the question of why the Kuiper Belt exists. The Kuiper Belt exists because its members never finished the process of becoming a planet. And they never finished that process because Neptune arrived and disrupted them before they could. The Kuiper Belt is the solar system's interrupted sentence, the thought that was never completed. We have been studying the Kuiper Belt seriously for only about 30 years. Pluto was discovered in 1930 by Clyde Tombaugh, but it was considered a lone oddball for decades. The idea that it might be the first known member of a large population of outer solar system objects was proposed theoretically by Gerard Kuiper in 1951, and even earlier by Kenneth Edgeworth in 1943, though Kuiper's name stuck to the belt. But it wasn't until 1992 that the first classical Kuiper Belt object beyond Pluto was discovered. The object is named 15,760, and its provisional designation was 1992 QB1. It's about 100 miles across and orbits at about 44 astronomical units. That discovery changed everything. Within a year, more objects were found, then more. By the late 1990s, the Kuiper Belt had gone from a theoretical construct to a confirmed, characterized structure with hundreds of known members. The rate of discovery has only accelerated since. What's remarkable is how recent all of this is. 30 years. One human generation. That's how long we've actually known that the Kuiper Belt exists as a real populated region rather than as a theoretical proposal. The detailed study of individual Kuiper Belt objects, the knowledge of their compositions, their internal structures, their geological activity, their moons and rings, all of that is even more recent. Most of what we know about Pluto, we learned after 2015. Most of what we know about Arakoth, we learned after 2019. The Kuiper Belt is not just an unexplored place. It's a barely explored place. We have sent one spacecraft specifically to study it. One. And it flew past two objects at high speed, unable to stop, unable to go back. The depth of our ignorance about the Kuiper Belt is significant. There are almost certainly large objects out there that we haven't discovered yet. The sky surveys that could find them only became possible recently, and they aren't finished. The chemical compositions of most known Kuiper Belt objects are characterized only crudely, from limited spectroscopic data taken at great distances. What Webb and Rubin will reveal over the next decade is likely to fundamentally reshape our understanding of this place. The Kuiper Belt is not a story we're at the end of. We're somewhere near the beginning. The first chapters written only in the last 30 years. The most interesting chapters still ahead. That's a good place to be. As a scientific community, there is a lot left to find out there. Consider one more thing about the scale of what we're discussing. The Sun produces a continuous stream of charged particles called the solar wind. Electrons and protons moving outward at speeds of roughly 250 to 500 miles per second, filling the entire solar system with this wind of energetic particles. The solar wind doesn't travel forever. At some distance from the Sun, it slows and stops, overwhelmed by the pressure of the interstellar medium, the sparse gas and dust that fills the space between the stars. The boundary where the solar wind gives way to interstellar space is called the heliopause. It's not a sharp edge. It's a diffuse transition zone. But it marks the boundary of the Sun's direct influence, the last point where the Sun's wind physically reaches. The heliopause sits at roughly 120 to 150 astronomical units from the Sun. That's roughly 2 to 3 times farther out than the outer edge of the classical Kuiper Belt. Inside the heliopause, the solar wind creates a protective bubble called the heliosphere. This bubble deflects much of the cosmic radiation that would otherwise pour through the solar system from deep space. Cosmic rays, high-energy particles from supernova explosions and other violent events throughout the galaxy, are partially shielded by the heliosphere. The Kuiper Belt sits well inside this protective bubble. The Sun's extended reach, in the form of its solar wind and magnetic field, covers the entire Kuiper Belt. The Kuiper Belt objects are bathed in solar wind particles, just very faint ones compared to what the inner planets experience. The magnetic field carried by the solar wind interacts with the surfaces of Kuiper Belt objects, contributing to the radiation processing that produces tholins over billions of years. And then there's cosmic radiation from beyond the heliosphere. High-energy galactic cosmic rays do penetrate the heliosphere, though in reduced numbers. Out in the Kuiper Belt, cosmic ray doses on a surface are higher than on Earth's surface, lower than in the outer heliosphere, where the heliosphere's shielding weakens, but still significant. These cosmic rays drive reactions in the surface ices that ultraviolet light alone cannot. Cosmic rays penetrate deeper into the surface, converting ices at greater depths rather than just at the uppermost layer. Over billions of years, this deep radiation processing alters the interior chemistry of the surface layer to a depth of several meters. The result is a stratified surface chemistry. The deepest layers, most shielded from radiation, retain chemistry closest to the original solar nebula composition. Intermediate layers show modification from cosmic rays. The uppermost layer shows the heaviest modification from both cosmic rays and ultraviolet radiation. Reading all 3 layers on a Kuiper Belt object would be like reading 3 different chapters of solar system history simultaneously. We can't do that yet. We don't have a lander, a drill, or even a spacecraft that can hover above a Kuiper Belt object and sample at different depths. New Horizons flew past. That's the best we've done. A mission that could enter orbit around a Kuiper Belt object, study it over months or years, and potentially deploy a lander. would transform our understanding of the outer solar system in the same way that the Cassini mission transformed our understanding of Saturn. Such a mission has been proposed. The scientific case for it is strong. The engineering challenges are substantial, but not insurmountable. The travel time to a Kuiper Belt object would be measured in decades, not years. The mission would need to operate autonomously through a communication delay of many hours. The cost would be enormous. Whether it happens depends on priorities, funding, and engineering advances that are still in development. But the case for it exists, and the information it would return would be worth every year of the wait. There's one more object that belongs in this story: Quaoar. Quaoar sits at about 43 astronomical units from the Sun. It was discovered in 2002 and is roughly 700 miles across, making it one of the larger classical Kuiper Belt objects. Quaoar is notable for something that surprised planetary scientists when it was confirmed in 2023. It has a ring, not unusual on its own. Haumea has a ring. Saturn has spectacular rings. Several other objects in the outer solar system have been found to have rings in recent years. What's unusual about Quaoar's ring is where it is. Most rings in the solar system sit inside the Roche limit of their parent body. The Roche limit is the distance within which tidal forces from the central body are strong enough to prevent ring material from clumping together by gravity. Inside the Roche limit, tidal forces win. Material stays as a ring, unable to accumulate into a moon. Outside the Roche limit, gravity wins. Material clumps together and forms moons. That's why Saturn's rings are inside Saturn's Roche limit, and Saturn's moons orbit outside it. Quaoar's ring is at roughly 2,500 miles from Quaoar's center. The Roche limit of Quaoar, calculated from its mass and density, is somewhere around 1,100 miles. Quaoar's ring is more than twice as far out as its Roche limit. It should not be a ring. By conventional understanding, the material should have clumped into a moon long ago. And yet, it's still a ring. The explanation being investigated involves the properties of the ring material itself. If the particles in Quaoar's ring are very elastic, bouncing off each other efficiently rather than sticking, collisions between them dissipate less energy. Less energy dissipation means less tendency for material to spiral inward or to clump. The ring might be stabilized by the physical properties of the icy particles it contains. At Quaoar's extreme temperatures, water ice and other ices may behave differently than ice does in warmer environments closer to the Sun. Very cold ice can be more rigid and more elastic than warmer ice. This is an active area of research. Quaoar's ring may be teaching us something about the physical properties of icy materials in the outer solar system that we didn't know from studying rings closer to the Sun. It may also mean that rings in the outer solar system can persist in configurations that wouldn't be stable closer to the Sun, a consequence of extreme cold on the material science of ice. Every discovery in the Kuiper Belt seems to find something unexpected, something that works differently than we thought based on everything we knew from studying the inner solar system. That is what makes it a frontier. Here is the full picture put together. 4.5 billion years ago, a vast disk of icy material surrounded the young outer solar system. It contained many Earth masses of material. Objects were forming throughout it, growing by accretion, working towards something larger. Then, the giant planets migrated. Neptune moved outward. It scattered the primordial disk, ejecting most of the material, locking some into resonances, leaving a depleted remnant. That remnant is the Kuiper Belt. The scattered material fell inward. It bombarded the inner solar system. The late heavy bombardment. It shaped the surfaces of the Moon and the other rocky bodies. It may have delivered water and organic molecules to Earth. It challenged whatever early life may have existed, but ultimately passed. What remained was the solar system we know, quiet enough for life to take hold on Earth, stable enough for complex organisms to evolve over billions of years, with a sparse, ancient Kuiper Belt as testimony to all that happened. The Kuiper Belt sends us comets. Some of those comets became meteor showers we watch every year. Some of them contributed to the water in Earth's oceans. Some of them brought organic chemistry that may have been relevant to the origin of life. And the Kuiper Belt contains frozen records of all of this. In the orbital structure that reflects Neptune's migration. In the surface chemistry that reflects 4.5 billion years of radiation processing. In the intact binaries of the cold classical belt that reflect the gentle accretion conditions before Neptune arrived. In the fragmented Haumea family that reflects an ancient, violent collision. In Quaoar's ring that shouldn't exist according to everything we knew before we found it. It is all there, waiting, in the cold dark beyond Neptune. We have barely begun to look. But what we have found already is enough to know that the edge of our solar system is not empty, not cold and boring and irrelevant. It is a place full of worlds, full of history, full of connections to everything that made this small, warm, inhabited planet possible. So, the next time you look up at a night sky and you can see stars scattered across the dark, remember what lies between you and all of that. Beyond the planets. Past Neptune's orbit. In a cold, dark region that receives a fraction of a percent of the sunlight that reaches Earth. There are worlds. Not distant galaxies. Not alien stars. Worlds. Frozen and ancient and enormous. Some of them have surface features more varied than people expected anywhere in the outer solar system. Some of them orbit the Sun on paths so elongated they travel to almost 1,000 astronomical units at their farthest point. Some of them are locked into gravitational step with Neptune, pulled into resonance by a planet that migrated outward and reorganized the entire outer solar system in the process. Some of them carry organic chemistry on their surfaces that may be related to the compounds that helped seed early Earth with the building blocks of life. And some of them carry the scars of a bombardment that shaped the inner solar system and may have determined whether life on Earth had the chance to survive at all. That's what's out there. Not emptiness. Not nothing. The Kuiper Belt. Violent past preserved in frozen chemistry. A record of chaos written in ice. A graveyard and a nursery at the same time. The real edge of our solar system is not a clean line. It is a place. A cold, populated, ancient, and incompletely understood place. And we have barely begun to look at it. Thank you for staying with me tonight. If this changed how you think about what lives at the edge of our solar system, about what the outer darkness actually contains, about what it means that those frozen worlds are connected to everything that made life here possible, then the time was well spent. If you found it valuable, a like or subscribe helps this channel keep making deep dives like this one. The universe doesn't run out of things to show us, and the strangest ones are often not the farthest away. Good night.